Mindsetters, you are here with me, Megan, on my second ever show here on Mindset Learn Extra. So seeing as that it's only my second show, I've decided that I will still do shout-outs, so don't judge. I know you guys still love me, okay? So I just want to say thank you and hello to Batoni Trading, my girls at work, and also far away in England, Blake Stead, hello to you. But other than that, grade 10s, do you know why you're here today? Is that longitudinal waves and sound that I hear? Yes, actually, I hope it is. But I know you've been on holiday and you're going to be right here with Tracy and I for a whole hour on physics, longitudinal waves, and sound. Tracy?
Thanks so much, Megan. We're going to be grade 10s. We've got lots to get through, and I'm hoping that today will be a great recap for you of work that you did last term with transverse waves, and we're going to be looking at some of those important concepts like frequency and wavelength. So make sure you've got your notes downloaded, you're ready and raring to go. We're going to be looking, as Megan said, at longitudinal waves and sound, and I want us to tackle some of the things we're going to look through today. We will define a longitudinal wave. Obviously, definitions are incredibly important in physics, and you know so much of the work that you do. You've got to know the theory, and then you've got to know how to apply that in practice. We will make a comparison between longitudinal and transverse waves. We have discussed transverse waves last time, but I say last time, and I know it was a few weeks ago, so go back and recap that. Then we're going to specifically look at sound. Now, sound is an example of a longitudinal wave. So we're going to discuss quite a few issues with sound and musical notes and things like that. And then we obviously always tackle problems, as you know, on Mindset Learn. So send us any queries, but pay lots of attention. We're going to go through quite a bit of theory before we get to some questions. So I want us to start with the demonstration. So I've got my trusty slinky over here, and I thought we could start with the demonstration. So I'm just going to hold this in my hands, and I'm going to hope that you will be able to see a transverse or a longitudinal wave. We did transverse a while ago. Transverse would be like that, where you're going forward and backwards while the wave moves across, or the coils go forward and backwards. What about a longitudinal wave? Longitudinal, let's go. So I'm going to go vertically. Waves could be going horizontally or vertically or at any angle. So I'm going to stretch it out and hope that you can see these little compressions as I bring my hand, that was a big one, as I bring my hand from the top down. So we're going to try to go a little bit more, just straighten a line. There we are. We've got quite a few there. Now, a longitudinal wave has got compressions and rarefactions. And if you turn to the board with me, we've got a couple of key concepts on the screen. Firstly, I've got a definition. A longitudinal wave is a wave where the particles of the medium move parallel, keyword there, parallel to the direction of propagation of the wave. Now I'm going to pick up my slinky again, and I want us to talk a little bit about what we've seen there. The particles would be the coils in this case. So as you look at my slinky, we've got the particles moving down as they are compressed, as my hand moves down. The wave, with that compression, moves down as well. They are moving in the same direction. And I've got a picture of this to show you. Now, it might seem I'm jumping. I'm going to come back to those notes. Here we have the particles being compressed. And there the particles are compressed. And there they're compressed. And the particles move in the same direction as the wave is moving. The wave travels down, the particles are compressed down and up, down and up. So the particles or the coils in this slinky are moving parallel to the direction of the motion of the wave. And that's by definition what is going to make the difference between whether something is a transverse wave or whether something is a longitudinal wave. Let's go back and compare them. So a longitudinal wave is a wave where the particles move parallel to the direction of propagation of the wave. So they're moving forward and back while the wave is moving forward and back, or backward as well. Now, we've had this word a medium. We used that a while ago with a transverse waves and transverse pulses as well. The medium is the substance that this thing is moving through, the wave is moving through. So it's a substance or material. What is the medium here? It's going to be the coils, right? In water, it would be the water particles. It's the substance that the thing is moving through, which the pulse or the wave moves. Now, I said at the start we would make a comparison and compare longitudinal and transverse waves. And comparisons are very important because they really help to clarify your understanding. Let's go through this one. We have a transverse pulse where the particles disturbed by the pulse or the wave move perpendicular. What does perpendicular mean? Big long word. At 90 degrees. So if I sketch here very quickly a transverse wave, the particles of the wave move up and down while the wave itself moves across. The particles there are moving at 90 degrees while the wave moves across. Whereas with a longitudinal wave, we have the wave moving across, but the particles themselves are moving back and forth parallel to the motion of the wave. Very important that you get that distinction. You need to be able to identify transverse waves and longitudinal waves. We want to label a couple of these regions of space in a wave. And so we've got two key words that I want us to pick up. And those words are a compression and a rarefaction. Okay? What is a compression? A compression would be the areas, and I've got this on the screen, so I'm going to work with it on the screen, would be regions where the particles are compressed, okay, most significantly. And a rarefaction, and I'm going to do, let's just unhighlight that bit. I'm going to do that in green. Rarefactions are these spaces where the coils are stretched out the most. So there's going to be spaces where they're compressed and there's spaces where they're stretched out. Compressions would be the regions in the longitudinal wave where the particles are closest together, they are compressed. Whereas a rarefaction, it would be where they are furthest apart, they are stretched out. Now let's consider some of the key words we've spoken about with regards to transverse pulses, and let's see, we've got some definitions for wavelength and frequency and period, etc. Let's go with some of those. The wavelength. The wavelength of a longitudinal wave is the distance, so notice here it is a distance measurement between two consecutive points that are in phase, i.e. it is going to be between two consecutive or adjacent compressions, or for that matter, between two adjacent rarefactions. So this could be one wavelength. That could be one wavelength. Sorry, that looks more like an X. Let's just undo that. One wavelength. Remember, a wavelength is simply the length of one wave, the distance for one complete wave. So you're going from point A to point B, a distance of one complete wave before another wave starts. The amplitude. Now, amplitude is a tricky one because it's quite hard to see this amplitude, which we think about, remember, as a height above rest. It's quite hard to think about an amplitude with a longitudinal wave. But what I want you to consider here is it's how far the coils, in this case, or the particles have moved away from where they originally were. So let's say if I've got this stretched out, if you've got a space where there's a compression, and I'm going to sketch this for you at the bottom here. If we have a bunch of particles, and there I'm going to draw my particles close together And here, whoopsie, put my slinky away. We can undo that. Here are those particles, and let's space them out kind of evenly. That's where they used to be. Then if I start to get them to be compressed, that guy is in the same place, and then his next one is next close, and then this one is very close, and then a little bit further away, and then he's in the same place, and then he's going to be stretched this side, etc. What you're going to find is if this coil was the third one, okay, it's been compressed a lot, moved far away from its original point. So what we sometimes do is you will find, and I know this might be confusing, but watch with me. If we put, say, on a graph, how far that has been moved away from its rest position, I would rather not put that there. What we can do is plot how far away the coils have moved from their position of rest. And some coils would be moved to the left, which might be negative, and some would be moved to the right, which we might call positive. And so sometimes in a test, sometimes you might find in some textbooks, they will actually draw a sound wave, which I know is a longitudinal wave, as a looking like a transverse wave. It's not a transverse wave. But what they are just showing here is that these particles have moved significantly away from their rest position. So they have an amplitude. So I said to the left was negative, so maybe let's draw something like that. Where the particles have moved away, far away, they're going to have the maximum amplitude. Where they've moved far away to the other side, a minimum amplitude. Okay? It is simply, if we go back to our definition, we know that amplitude is the maximum displacement from equilibrium, which we know is rest. So this would be the maximum increase or decrease in pressure. If I'm thinking about air pressure, that's another example. If I've forced particles to move away from their original position, you are then resulting in a maximum increase or decrease in pressure. That is caused when a compression or a rarefaction passes a point. So those particles, if they're compressed, they're going to be moved away from rest. And we can plot that vertically. You're then plotting not the wave passing, but what you're plotting is how far away the coils have been forced to move. Okay? And yes, they're moving parallel, but we can plot how far on a vertical axis. So it can be tricky, but I think that's helpful. Over to the next point, we've also got frequency and wave and period and the speed. The frequency would be the same as what we had for transverse. How many waves pass a certain point in 1 second, per second, so in 1 second. The way of a wave is the number of wavelengths, complete waves passing in a second. The symbol, we have the same frequency measured in hertz. That is also, remember, the inverse of the period. So the period of one wave is the length of time it takes to get for one wave to pass, for one complete wave to pass. Remember, we had this equation, frequency is equal to 1 over the period or time, and then the speed of the wave. Again, exactly the same for transverse waves. This is a recap from last term. What you have here is the wave speed is the distance the wave covers, that it travels per unit time. So just like in a car, you would be going in kilometers per hour. That's a distance divided by a time value. We would also have here meters per second, meters divided by seconds, the idea of a distance divided by a time. So I have an equation on the board of very important equation. The speed, which is given by v, is equal to the distance traveled. The distance of one complete wave is its wavelength. And the time taken for one complete wave, remember we said, was the period. Now, that's going to be very useful to me, but we can convert that equation very easily if we have, and I think I'm going to need some more space, so I'm just going to move down to the bottom. If we have there already V is equal to lambda divided by time, the period, that is the same as saying lambda multiplied by 1 divided by the period. Okay, and then what we've got next is we're saying, but hold on a moment, that is the same as frequency. 1 over the time, 1 over the period, should I say, is the same as the frequency, so I can plug in lambda multiplied by frequency. And that is the classic wave equation that we use all the time. The wave equation, something you need to know. And then to finish off, I've given a summary of the physical quantities that we've talked about. Notice amplitude is a distance measurement. It's measured in meters. Wavelength is also a distance measurement. It's measured in meters. It's how long one complete wave is. The period is a time value, so it's measured in seconds. The frequency is the rate of this, it is the 1 over the period, so it's going to be per second in hertz, and then the speed, the wave speed, is in meters per second. So I hope that's going to help to summarize what you've looked at with regards to waves and specifically longitudinal waves. We're going to take a break now. So over to you, Megan.
Wow, I can't believe it. It went so quickly, but I'm so sorry. Mindset is, I was so eager that I was doing my own show. I didn't even tell you where to contact me or us. So Tracy and I are going to be now in the ad break looking at no questions. So please contact us on facebook.com/learnextra or hit us up on Twitter @learnextra. Or if you want to be really smart, don't forget you can download all the notes, tutorials, and videos at www.learnextra.co.za/live. So enjoy your break and come back with lots of questions because I'm so eager and Tracy is so eager to answer them. So enjoy your break and I'll see you afterwards. Hello Mindsetters, welcome back. You're here with me, Megan, and we are doing grade 10's longitudinal waves as well as sound. So I hope you got a little bit of a break because what we're going to be doing now is hard-hitting stuff. So please take your notepads and your pencils out and write all of this down. Or if you have any questions on what's going to happen now in the next few minutes, please hit me up with some questions at facebook.com/learnextra or @learnextra on Twitter. So over to you, Tracy. Let's go.
Thanks, Megan. So Mindset, as we've been starting with longitudinal waves, we're now going to move into sound, and sound is a great application for longitudinal waves. So we're going to be looking at quite a couple of questions as well, so do stay tuned. Longitudinal wave. Now again, I've got the definition there. A longitudinal wave is a wave where the particles in the medium move parallel to the direction of motion, of propagation of the wave. And we specifically are speaking now about sound waves. Sound is a pressure wave. Sound waves, very important, are pressure waves caused by objects which are vibrating. So maybe it's going to be this little tuning fork that I've got that we would hit and it starts to vibrate. And what it does is it causes the air particles in front of it to be compressed. As it's moving forward, it's causing them to compress together, and then it starts to move backwards. And the next part, the air particles next to that, then stretch out, and then they get compressed, and then they get stretched out. And so that is how the wave is propagated. So here we have a compression, and then a stretching out, and then a compression, and then a stretching out. So those are compressions and rarefactions. Compressions, rarefactions, and so the wave is propagated. So these are actually pressure waves which are caused by objects that are vibrating, that are moving. Now, it might be a loudspeaker, and I'm sure you've seen a big loudspeaker pumping out the sound, and it moves forward and then backwards, forward and backwards, and so the air particles are compressed and stretched out. Another great example, a guitar string. As a guitar string is plucked, it vibrates and sends out air particles. Maybe you've even done this, put a ruler on a bench and hit it, hopefully not breaking it, and you can see the vibration of that ruler and you can hear the sound. So always sound waves are caused by objects that are vibrating. But here's the interesting bit. Sound waves need a medium through which to travel. Because they are pressure waves, the wave being transferred, the energy being transferred is going to be passed on to the next particle, but there have to be particles to pass that energy along. And you can go on YouTube, some videos, there's some great videos where you can actually see an alarm clock, you know, one of those old alarm clocks with a bell that's vibrating, and you can set it on and you can actually see it moving. But if you suck all the air out of the container, you can see that it's vibrating, producing a sound, but you can't hear any sound. And that is because the particles pass on their energy to one another. But so there has to be particles moving in there to move and pass on the vibration. As the source of the sound vibrates, it creates regions of high pressure. We've already mentioned this. High pressure and regions of low pressure. Those would be the compressions. And the low pressure would be the rarefactions. Okay. What about the speed of sound? Well, the speed of sound depends on the medium, because remember, the medium is what is passing on the energy. Okay, so as the one particle gets energy, being passed on to the next, being passed on to the next. So let's talk a little bit about the speed of a wave, and specifically not just any wave, but a longitudinal wave in a medium. Well, there are three things that the speed of sound waves depend on. Firstly, on the phase in which the medium is in. Now, phase, I mean the state of matter. I mean, is this thing a solid, a liquid, or a gas? Okay. So for a solid, think about what a solid is. The particles are closely packed together. And recall, this is going to reflect back onto what you learnt right towards the beginning of the year on the kinetic molecular theory. So go and catch up on the kinetic molecular theory, where particles for a solid are closely packed together. For a liquid, remember, they're not so closely packed, they can slide across one another. And for a gas, they're far apart and moving very quickly. So let's reflect back onto solids. Well, we've already said that solids are closely packed together, and so what that's going to mean for sound waves is that this solid particle, I'm going to pretend to be a particle, vibrating around, and it passes its energy on to the next one, and it's passing the energy on to the next one very, very quickly. Okay, so here sound waves move fastest in a solid. What about temperature? Okay, and obviously then, sorry, let's go back to solids, so obviously then less in liquids and even less in gases. If we go on to temperature, the higher the temperature, the particles move faster. They have higher kinetic energy. Now this is also reflecting back onto what we learned with the kinetic molecular theory. And we had this idea that if you increase the temperature, the particles move faster, and so they will then be able to pass their energy on to the next particle faster. So here, higher kinetic energy because of higher temperature is going to mean that the sound wave is transferred and propagated much faster. What about air pressure? Now, if we have got the stuff as a gas, then if the gas is compressed where the particles are closer together, okay, that's going to mean that the energy will be transferred along even faster. So higher air pressure is going to mean higher speed of the waves. They will be moving faster. Now, where do we get that? My sentence is not particularly good here. It would be found at sea level, where the air is denser. Now, at high altitude, up on a mountain, or even here if we think about in South Africa, areas inland, particularly significant inland at altitude, like in Johannesburg, at high altitude, the air is thinner, which means that it is less dense, and so sound will not travel as fast. Whereas at sea level, the particles, there's a far, far higher air pressure, and so therefore the air is denser and is going to pass on and propagate that sound wave much quicker. Let's take this and go and answer some questions specifically on sound. So over here I've got question 1, because I know you're burning to answer some questions. And we've got a flute, a little flute making a musical note, and they tell us that it's traveling at 320 meters per second. So immediately I'm writing V is equal to 320 meters per second. The frequency of the note, they tell me frequency is equal to 256 hertz. Calculate, point A, the period of the note. Now, what is the period? The period is the time for one complete wave. And the equation for this, well, the only equation that I can work with, or one of the equations I can work with, is the period is equal to 1 over the frequency, or that is the same equation, I've just rearranged. Frequency is equal to 1 over the period. So I already have the frequency. I'm going to just be able to plug in. So here we have 1 over my value of 256, which is, and let's go to our calculator, 1 divided by 256. Or many of you might be wanting to just go straight into using your fraction button. That's absolutely fine. You'll get the same answer. And here we have, sorry, I needed to remember that number, 3.91 times 10 to the negative 3. So coming across 3.91 times 10 to the negative 3. What unit will I use? Well, it's a time value in seconds. Let's give us some more space. And now we need to work out the wavelength of the note. So I'm going to write my values down again. I had V is equal to 320 meters per second. I had 320 meters per second. I had frequency was, let's find what it was, 256 hertz. I also now know the time, which is above, the period, sorry, but I don't think I'll need that because I've got two values that will work very well. The equation, the classic wave equation, V is equal to lambda times frequency, and I need to rearrange this. Now, I want to solve for lambda, which is my wavelength. So what do? V divided by the frequency. Why? Because I know that on this side of the equation, this was multiplying. So when I take it across to the other side, it must be dividing. So that is leaving me with lambda, and now I can plug and play. We've got 320 for my speed divided by my frequency, which was 256, is equal to lambda, So let's go back to my calculator, and I'm going to just clear this. So 320 divided by 256 equals 5/4. I want to always give my answer in a decimal. The reason for that is because a fraction is just abstract, whereas in science we're working with real numbers. So let's write that down. 1.25 is equal to 1.25. What is my unit going to be? Well, it is a distance value, so in meters. And that is the wavelength of the wave. We're going to take a short break now, and when we come back, we're going to be tackling lots of different problems with regards to the applications of sound, and specifically in musical notes. So don't go away. Megan, over to you.
Thanks, Tracy. Well, it seems that you guys are getting quite a few of the things. Those who did post questions, I will ask Tracy now during the ad break and get back to you on Facebook. But quickly go to the bathroom, get something to drink, and then we'll be right back with some more physical sciences for you grade 10 mindsetters. Welcome back, grade 10 mindsetters. So you're here with me and Tracy on our physical sciences lesson with longitudinal waves and sound. And we've been going for about 40 minutes now, so I know you guys are biting just to get to all the questions. So Tracy and I did discuss some questions, and I'll be posting them on the page. I see some of you are asking me now, where can we get the questions? What is happening? So don't forget, if you want to contact us on Facebook, it's facebook.com/learnextra. Or if you want to download all the notes and be a smarty pants, then you can go onto our website at www.learnextra.co.za/live and download all the notes that we have right in front of us that Tracy's going through. So let's get back to it.
Thanks so much, Megan. So mindsetters, we've spoken through a longitudinal wave and a transverse wave. We've compared the two, and we've then said that sound is a longitudinal wave. Now remember, a longitudinal wave, we're saying the particles are moving in the same direction, or should we say parallel to the direction of motion of the wave. So the wave is moving across, they're moving forward and backward in the same plane of motion. Then we've spoken about sound waves, and from sound waves we looked at a question, and we specifically are thinking now about applications of sound. So I wanted to start off with echoes, and I'm sure you've heard this before. Maybe you could walk into a hall and you suddenly hear the hall is empty, and you can suddenly hear your footprints at with your shoes steps as you're going through into this empty hall, and it's echoing. Or maybe you've gone for a long walk and you've seen a big cliff, and you can go hello, and you hear hello come back to you. Okay, that is an echo, and an echo is just a sound wave getting reflected off a smooth surface. In a hall, when there's not other people around and not lots of other interfering noises, you can also hear reflections off the smooth surfaces of the wall. So we're going to look at a question on echoes, and I want you to focus here on the idea that because it's a wave, it has the properties of a wave that it reflects. So as the sound wave passes through, hits something, bounces off, and comes back to you. Okay? You can hear the repeats, and I put here of the hello, hello, coming back at you in maybe a split second later. Or if you clap your hands, and that's another great one, a nice clear clap of the hands, you can hear that coming back to you. This reflecting property of sound waves is used in sonar, and we'll talk about that, by animals like bats and dolphins. And I'm sure you've seen a bat, you might have seen a bat in a picture with those very big ears. The big ears are helpful because they would collect lots of sound waves, and that's how a bat would detect its surroundings. As it's taking in all these sound waves from its surroundings, it's going to make up the picture of what is around it. Okay? And then dolphins as well. And dolphins have quite a high-pitched sound that they send out. And that is useful for them in what we call echolocation. Now, echo would be that reflection of a surface, and location to help them find out what's around them. Okay, so a nice key word there, echolocation. And in the same way, a boat can use what we would call sonar. And I'm going to draw a little picture of a boat. So there's the waves of the boat, and the boat is sitting in the water. Okay, and it can send out waves, sound waves, and let's draw the surface down the bottom there. And what it can do is it can send out sound waves that then hit off the surface of the ground and get reflected back to the boat. Or even, let's get this one further, get reflected back to the boat as it hits against the surface. Boats can also use sonar to go and find shoals of fish, schools of fish. And that's how a lot of the fishing is done nowadays, because they can send out sound waves, and those sound waves bounce off objects underneath the water and get reflected back to the boat, and they would have a receiver that would detect that, and they can work out how far away the object is, okay, or the surface of the floor. And that's one of the ways in which scientists are discovering what's underneath on the surface of the ocean floor, underneath the water. And we can go really deep down because we can reflect these sound waves back. Okay, sonar, very, very useful tool. Let's look at a question that is based on this. Now, I have got a question here. Calculate the speed of sound in air. All right. And I played with these numbers a bit, so they're not going to give us nice values. But if it takes 1.3 seconds for you to hear an echo, so immediately I'm writing my list, time 1.3 seconds, and I'm going to say here, to hear sound. Okay. Let's go back. For you to hear the sound. For you to hear an echo, when the distance from you to the reflecting surface is 450 meters. So let's go down. X, the distance is 450 meters. So imagine we shout out, hello, and these waves going past. They should be equidistant, but these waves are going along. They get to the wall, and I'm just going to draw it with arrows, and they bounce back to you. Okay? The question I have before we tackle this problem is, if the time that it takes for you to hear the sound coming back to you is 1.3 seconds, how long did it take for the sound to get to the wall? Think about that. How long did it take for the sound to get to the wall? The question is really saying the whole distance that sound traveled was from you to the wall and back. So this 1.3 seconds that we're highlighting is actually the time it's taking for the sound to travel twice the distance. Okay? So in order for me to calculate speed, and let's go with our calculation now, it's going to be velocity is equal to displacement divided by time. Now, I'm going to change that into symbols, and I'm going to say delta x divided by delta t, the time it's taken. So here what we have there is the distance it's covered, and the distance it's covered is there and back. So let's do this in two different options in terms of calculating here. What we could have, option 1, would be to say, okay, my delta x is equal to 450 meters multiplied by 2. Why is that? Well, because I know that this distance was 450 meters, and it's had to go there and back, right? So option 1, and time was my 1.3 seconds. So let's plug in the values. V is equal to delta x over delta t, 450 times by 2 divided by 1.3, and I know that that's 900 divided by 1.3. Let's go grab our calculator. Just check me. 450 times 2 is equal to 900 divided by 1.3 is equal to, sorry, I need to go back there. The value 692.3. So let's get my answer there. 692.31, I think it was, and my unit meters per second. Okay, now that's actually exceptionally high. My numbers don't work that great, but let's carry on with option 2. Option 2, if we say that the distance is 450, I need to make sure that I'm halving the time, because if you think about it, that's now the time it took to just get halfway, just to the wall. Okay, so my time is now 1.3 divided by 2, which is going to be 0.65 seconds. As I then work through the calculation, V is equal to delta x. Always write your equation, please. We have to make sure you have an equation, because science, you are proving something. So it was 450 divided by 0.65 seconds, and that was meters. Gets me, well, let's go back to our calculation. I'm clearing that, and we're going to go 450 divided by 0.65, and we come to exactly the same answer, 692.31. So as I go back here, we've got 692.31 units. It's speed, so meters per second. The focus here I want you to identify is that there are lots of options. There's lots of ways to get to your answer, but you need to consider, going back to the question, that you are covering, for that time, it was covering the distance twice, right? Or because it had to go there and back. And with echo problems, you're going to need to really think through how you work these out. So I want us to move on a little bit to some key concepts, and I've written a note for you specifically because I know many students struggle with these echo problems. I've put the equation there. Remember that the distance traveled by the sound wave is twice the distance away from the reflecting surface, from the wall or from whatever other object is reflecting. Okay? And when you do this, just think about, maybe draw a picture. That's probably your best bet, because you can quite quickly see that the distance is going to be double. Okay? Or the time you need to work with might be halved. But you need to go and identify the question that you're working with. Let's go through some other properties of sound. You might often hear of the word pitch. The pitch of the sound relates to the frequency, and that's critical. So pitch, you're thinking immediately the frequency of the sound wave. For example, middle C on a in a musical note is given by 256 hertz. The higher the pitch, the higher the frequency. So I've got two sound waves here. Sound A has a high frequency, and sound B has a low frequency. What we would notice here is high frequency or high pitch would sound really, really high. Low frequency would sound really, really low. Okay? So frequency is related to the pitch. Have a look at what the picture would look like. Here we have the frequency, the wavelength looks quite a lot smaller, whereas for sound B, the wave looks like it's been stretched out a bit. It's got a low frequency. In terms of what we can hear, our ears can detect a wide range of frequencies, from 20 hertz to 20,000 hertz are audible to the human ear. Any sound below the 20 hertz, so below the threshold of what we can hear, is known as an infrasound, and a sound with a frequency above that 20 hertz, that 20,000 hertz, is known as an ultrasound. Okay, very important. Just to know those thresholds, what we can as humans detect. Then we need to look at the last one, is loudness. The loudness of sound relates to the amplitude. Now remember here we're getting some pictures that look like they're transverse waves. They are not transverse waves. Sound is not a transverse wave, it's a longitudinal wave. But in terms of its representation on a graph, what they've done is said how far away must those particles have moved to get the maximums and then therefore the minimums as well. So it relates to the amplitude of a sound wave. The higher the amplitude, the louder the sound. So I've got, again, two waves, and I want us to look at them a little bit closely. This is from my rest position, Sound A has its amplitude. Sound B has its amplitude above that dotted line. So this is a much louder sound. Okay? So the two that we've gone through, pitch would be related to the frequency, the loudness of the sound related to amplitude. And amplitude, if you listen to very loud sounds, the amplitude is very high, it can actually cause damage to your ears because your eardrum is vibrating substantially, and that can cause significant damage. So watch out for loud sounds. That's all. That will round off our section now on frequency, wavelength, all these different ideas related to sound. And remember, sound is a longitudinal wave. So go back and make sure that you can recap all those ideas, and I hope that that's been incredibly helpful to you, grade 10s, as you're working through all these new important concepts. Good luck and enjoy. Thanks, Megan.
Tracy. Well, I must say, I haven't been in grade 10 for 4 years now, and we used to do that, and I learned way more in this lesson than I ever did at school. Sorry to say, but anyway. So mindset is you were actually very, very quiet on the page. So I don't know if it's because Tracy was explaining it so well, it must be. I mean, there's no other reason, right? I know. So anyway, I've decided that each show, I'm going to wear a different headband. Don't ask, it's just my thing. So if you think it's weird or you think it's cool, just let me know. And that's how we can all become friends, because at Mindset, aren't we all about helping each other out, learning more, learning extra? I think so. So if you want to download all the notes, please, if you want to be a nerd like myself, then go to our website at www.learnextra.co.za/live, or you can hit me up on the Facebook page at facebook.com/learnextra. So I'm going to be here for the grade 11 show. So grade 11s, I hope you are tuned in for Refraction, all about light and whatnot, because it's part of our everyday. So I hope that you stay tuned in with me, and that's love from me to you, grade 10s. Cheers.